Alright, so in this group of practice problems, we have a series of mass spectra, and our goal is just to come up with formulas that fit the spectra. Doesn't mean we're always going to come up with exactly the right formula, but we just want something that's going to be consistent with the information that we have. And so in the first four of these, we have just the MS, but in 5 and 6, we're going to be able to go a little bit further because in addition, we also have the IR spectra given to us. So largely what we do here is going to be based on the parent peak. In this first spectrum, we can see our parent peak out here at 142. So what might we have here? Well, we know it has to be less than 12 carbons, because if we have 12 carbons, that would be a mass of 144. And that's more than what we have for this compound. So we could go down to 11 carbons. That would be 132 plus 10 hydrogens. That would work fine. Or we could go down to 10 carbons, which is 120, and that would leave us with 22 hydrogens. Either one of those work and would be a correct answer given that we don't have any other information about this molecule. We have a very similar situation in number 2. We have a parent peak at 120, but not a lot of other information. Now 120 is exactly 10 carbons. But it's pretty rare to have a molecule that has only carbon in it. So we would probably disregard that. But if we go down to 9 carbons, that's equal to 108. We would need 12 carbons to get us to 120. We can't go any lower than 9 carbons unless we start adding other atoms, because if we end up at 8 carbons, that's 96, which would give us 24 hydrogens. Now, how would you know that a formula like this doesn't work? Well, you could always calculate the degrees of unsaturation. For C9, and we can do that for all three, if we did C10, it would be 2 times the number of carbons plus 2 divided by 2. That would mean we would have to have 11 degrees of unsaturation. Not impossible, but not terribly likely either. For C9H12, 2 times 9 plus 2 minus 12 divided by 2 is 4. It's a very reasonable number of degrees of unsaturation. In fact, that's exactly equal to what's in an aromatic ring. So that one very well could work. But this bottom one, 2 times 8 plus 2 minus 24 divided by 2 is equal to -3. And a negative number of degrees of unsaturation is not possible. So if you ever do something that gives you a negative number of degrees of unsaturation, you know you've done something wrong. All right, number 3, our parent peak is here at 101. Well, 101 is an odd number. That tells us we have a nitrogen in this molecule. That leaves us with 87. If we went to C7, we'd only have enough room left for 3 hydrogens. And so while that certainly does add up, it doesn't add up very well. Again, we usually have very similar numbers of hydrogens and carbons in a molecule, or the number of hydrogens is larger. But to have number of hydrogens this small compared to the number of carbons is pretty rare. So what if we go to C6? That's equal to 72. That would leave us with 15 hydrogens. Does that work? Well, we can do what we did on the previous one. 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogens divided by 2. In this case, we get 0 degrees of unsaturation, so that is an acceptable number. It just means we don't have any pi bonds or rings. It could be a molecule that looks like this. And we found a chemical formula that works with the data given. All right, in number 4, probably the first thing that's most challenging is to find the parent peak. It's here. It's just very, very small. But if you look carefully, it's right there at 178. The second thing you might notice is we have these two peaks here that are 2 mass units apart at a ratio of approximately 3 to 1. So we can be fairly certain that we have a chlorine in this molecule. So now we can take our 178 and subtract out the 35 for the chlorine. Leaves us with 143. Again, 12 carbons equal 144, so that's going to be too many. But if we have 11 carbons, that would leave us with 11 hydrogens and our chlorine. All right, as we go on to these that now have multiple spectra, I often find it's easier to start with the IR spectrum. And this IR spectrum gives us one clear thing, one clear functional group. The alcohol. Now, if we go up to our mass spec, we see our highest peak here is at 100. But who recalls what we said already about alcohols? We said about alcohols that they fragment very easily. And they fragment in such a way that they usually lose 18. So the actual parent peak here is not likely to be 100 because of the alcohol. It's much more likely to be the 100 that we can see plus a molecule of water. So most likely here the parent peak is at 118. If we subtract out the 16 for the oxygen, we're left with 102. And then we could try 8 carbons with 6 hydrogens and an oxygen. That works. Or we could go down to 7 carbons. Well, if we go down to 7 carbons, that means we're going to need 18 hydrogens. And that's too many. Again, we could look at the degrees of unsaturation. 2 times the number of carbons plus 2 minus 18 over 2 gives us -1. So we know that this one doesn't work. And finally, we have one more. The first thing that I see in this spectrum is we have a carbonyl. Most likely a ketone given the 1709 wave numbers for it. Looking at our mass spec, our parent peak is at 107, which also suggests that we have a nitrogen. So if we subtract out the nitrogen and the oxygen, that's equal to 30. Which leaves us with 77, which would be enough for 6 carbons as well as 5 hydrogens. So basically, when you're approaching one of these problems, you want to approach it in such a way that you account for any functional groups that you know of, or halogens. We can see nitrogens, we can see halogens in the mass spec. If we have another spectrum that goes with us, account for any functional groups that are there. And then find a combination of carbons and hydrogens that's valid. And how do we check to make sure it's valid? Well, one of the easiest ways is what you saw me doing here. I plugged the formula that we came up with into the degrees of unsaturation. And if I came up with a negative number, then I knew it wasn't possible. So that brings us to the end of mass spec. And after this, we're going to get into what I would say is our most important type of spectroscopy, which is NMR.